right, thank you, everyone. So, for many, many years, more than 15 years by now, I've been working with my team on a lot of application security, right? Per the introduction, a lot of bugs, vulnerabilities, various different methods. How can we determine these types of issues through software techniques? And now, as a result of that, like in recent years, we've been thinking about how can we make application security more intelligent? And how do we move towards that aim? So I'm Cristina Cifuentes from Oracle. And of course, this doesn't want to work. Wait, sorry. OK, there we are. So these days, we are all living with intelligent applications, right? You're typing your email, and the email client is already telling you how to autocomplete the rest of your sentence. You're writing a text message, and same thing. Here's the suggested next words that you can use in your particular text message. What about software? Now, for software, there's a lot of different types of applications that are out there already. For example, like Visual Studio IntelliCode, like you're typing some new piece of code, a replacement dot, and as soon as you put the dot, it's suggesting for you, here's all of these different methods that you could use. And these methods are kind of like the auto-completion, right? These code completion suggestions, purely based on training that has been done over thousands of open source projects. Now, what about Aroma? In this case, you're typing your code at the left-hand side, and you want to have a bitmap factory decode stream. So Aroma actually goes and proposes to you, it recommends 2 or more different pieces of code that you can use as templates as to whereabouts and how other people have actually used bitmap factory.decode stream. So you can select one of them and then keep on using it. What about LLMs? Of course, these days, you now have small suggestions of pieces of code purely based on comments or on code that is within the application that you're writing. So in this particular example, GitHub's Copilot, it can actually generate for you 10 up to 15 lines of code, and in various different languages. And very similar, Amazon's Code Whisperer would generate also those 10, 15 lines of code. They base it a lot on a lot of the comments that you have in your IDE, but also on any prior code that you've written in their system, right? But beyond just writing some of the code or helping you write the code, there are other applications that exist already, right? You have CodeGuru's Reviewer, where it actually goes and reviews code that you have written. And in this particular case, it focuses on identifying very critical issues and performance issues. And of course, finding performance issues can be hard. They make the recommendation hey, this particular statement, you should be implementing a very different pattern that is going to save you performance overall. What about testing? We all know testing takes a lot of time. When you're testing your mobile applications, Android in this particular case, Sapiens developed this technique whereby they can automatically generate many, many different tests for your Android applications, purely based on system testing. And here you're seeing more than 100, right? The different tests that they automatically generated, and they also are running in parallel for you to be able to do your testing much more quickly. And let's go a step further. When you do tests, you find bugs. And there are very simple techniques, get a fix, where they actually go and look at code that is very localized, so lint type of bugs, and they would go and tell you, hey, there is a bug here. here's like this little piece of code that is actually going to fix that particular issue for you. And in this particular example, the lint that was found was a null method call. And so they have 3 lines of code there that they suggest for you to be able to fix that particular issue. And then we all know that when commits get pushed out, and you have your code going out, performance regressions can be introduced. And so there's this bug to commit system that actually looks into how to track, once you've pushed out your application, how to be able to determine where there has been a performance regression and be able to feed that back, that information back, so that then you can go and look into, well, the system will look for you into which particular commit was the one that ended up generating that particular performance regression and be able to help you out, revert that particular issue. And last example of existing applications that are relevant here is Code Group Profiler. You have an application that is already running. You can imagine you have a cloud system. It is running, you're paying a lot of money, and this particular tool actually goes and looks at what are your most expensive lines of code. And it makes you aware of them so that you can then improve your code and be able to pay less in this particular case. But it actually recommends for you improvements purely based on how often certain lines of code are being executed, right? So what does this mean for DevOps, right? If I take all of those examples that I've shown you from a variety of different types of companies, you can then map them into a standard DevOps model, and you can start seeing like, oh, we can group like a lot of the first examples that I talked to you about that purely relate about code into what I would call this is intelligent coding, right? You have your IntelliCode, the Aroma, Code Whisperer, Copilot, Code Guru Reviewer, get a fix, right? It's helping your developer be more intelligent, right? What about like testing? There were several examples that we can group into intelligent testing, right? Like there was Code Whisperer, there was also Sapiens, get a fix, that was actually even helping loop back into the coding by proposing a fix, and the back to commit, right? And then on the right-hand side, I gave you like one example of something that would be equivalent to intelligent monitoring, right? As your application is running, it is monitoring your application to then be able to provide you with recommendations. Now, of course, in order to do this, you need to have some type of knowledge base on your top right-hand side, right? To be able to keep track of information that these applications can actually make use of. And for a lot of the examples that are listed here, well, for a subset of them, well, you will make use of GitHub, like it's a lot of training that is happening through open source repositories that are in GitHub. You can also track things from Jira and from a lot of other places. So in this talk, I wanted to focus more on application security. And with application security, if you really look at where it came, right, like the legacy of where it came, everything was in terms of application security testing. And over the past 15 years, we've been doing a lot of different pieces of work to kind of like make a change so that it's not really only looking at testing, right? And so this is an Oracle Labs perspective. So when you used to look at the waterfall model, right? There's where this application security testing, the testing component came from, in that you had techniques that were developed that people thought like, oh, we can integrate them at the testing time. And techniques like SAST, like static application security testing, and DAST, dynamic application security testing, their names derive from that, right? And so everyone used to think like, oh, okay, like when we do testing, then we'll integrate these techniques and so on. Clearly, those techniques were being integrated far away from where the developer is, right? Developer would develop code. Testing used to be done by a different team, your QA team. So when we looked into static application security testing, and this was work that we started probably 15 years ago, 16 actually. Some of the challenges that we were seeing was that a lot of these tools were reporting too many false positives, right? And so that was an issue for developers in order to be able to use them on a day-to-day basis, integrated into their code. The other biggest problem was that a lot of these tools back then, so this is 2017 and 2016, they were taking more than a nightly run in order for the tool to provide you results. And so me as a developer, I would have to wait more than one day, and by then I've already written other code, and it was hard to integrate some of these techniques. So one of the things that we looked into very early into the process was, how can we make this process more efficient? Clearly, the earlier that we can do some of this testing, right, by integrating into your build, the better. But for that, you need to be very efficient. Like your analysis techniques that would report bugs or vulnerabilities need to be very efficient, because otherwise doing it in the nightly run, you need to ensure that it actually completes, right? That is going to take a day up to 1 week, right? And so in yellow on the bottom right-hand side, I have papers that we have written that explain some of the techniques. I'm not going to go through the techniques in this particular talk. But one of the things that we focused on was on how do we make scalability really happen. And even though the techniques that we have implemented do deep static code analysis by doing interprocedural data flow analysis, right, and looks at complete code bases that are millions and millions of lines of code, you can see in this slide that looking into 2 different languages and taking large representative applications like the Oracle Linux kernel or a lot of different cloud services that have been written in Java, you can see that the runtime for the analysis is pretty fast, right? In order to be able to do full analysis of all of the bugs that you can find over 16.5 million lines of code, to do that in 20 minutes, that's significant, right? That's pretty fast. You can definitely be able to run this more than once a day, but at least you can run it once a day, right? What about your cloud services being able to run over various different pieces of Java code in 7 minutes? Again, same, significant. You can actually integrate these much closer to the developer rather than doing it later. Some other team will do it later, right? And the other point that we focused on was on the precision, right? That too many false positives. That's what a lot of people think about a lot of the static analysis tools. And we went for the other way around. We're how do we ensure that precision is actually good? Because the more precise you can be, of course, the better, because then the developers are going to go through less type of issues, and they're going to be more quickly be able to determine, hey, I really need to fix these things. Whereas if you're generating a lot of noise, developers will just give up and say, hey, this is a tool that I need to not pay attention to. So with this, what you can see in the graph is the fact that over a period of 6 different years, we were tracking very large internal organization. And you can see here that, when you first run the tool, you end up with a particular baseline, right? Here's all the different bugs and vulnerabilities that the tool found. But you can see that over time, developers actually ended up fixing these issues, right? And if we take this other peak, you can see that it got almost close to 0. You take this other very high peak, and it went almost down to 0. And so what's happening there is that you're seeing an organization that is actually actively taking the results of these various different bugs and vulnerabilities and fixing them, because they do believe in what the tool is telling them. The tool is actually telling them useful things. You also see at the same time that there are some peaks that were generated here after various different bugs had been fixed. And that's, of course, because new bug types get introduced. This particular largest peak was a particular bug type that was introduced at the request of that particular organization, something very specific to the type of code that they write. But very useful to them to be able to catch all of these issues early in the development process. It means that the issues are not going to happen, at production time. So then the other advantage of being able to try and get things like closer to the developer, and we started doing all of this work before people were talking about shift left, but effectively that's what we were doing. We went, hey, we can get this closer to the developer so that while they're developing code, we can actually just look into the change set of code that they're going to integrate into a commit and be able to do the analysis efficiently at that point in time. So in order to explain a little bit on high level how this would work is that by default, if you do like a full run of our static code analysis tool, Parfait, you would take like all of your different files. The tool would actually generate a certain number of defects for you, but at the same time, it will create function summaries for all of those files. So what that means is that if I'm a developer and my change set was only, let's assume, one file n that I want to run, then in order for the tool to be able to determine if I have new issues in my change set, it would look at that file n, but it also needs to look at any dependencies that my file has on other files. And there's where it can pull function summaries of dependencies that I have on other files. And let's say that the dependencies were 4 files, and then be able to do the analysis amongst those 5 files to be able to have complete view of what it needs in order to get a precise type of result for you and generate that, any defects that may happen in that code base. So that means like when you look at doing a full scan versus doing like a change set scan, you're clearly looking at very different numbers, right? Like in C, a full scan that would take 15 minutes, when you look at a change set, it would only take 2 to 3 seconds. In Java, if you have like a 15-minute scan for the full application, when you look at change sets, at the time that we developed these techniques, it was taking 3 to 5 minutes to do that scan, just because Java is more complex and has like more method calls, dependencies, inheritance, and so on compared to the C language. But in any case, you can see how that pushes things to the left. And what that means is that organizations can actually introduce these tools and be able to integrate them even before the commit gets done into the code base. And so this is the same organization starting like kind of like in 2012 instead of 2011, which was the earlier graph, because at that point in time, they went, hey, we want to start tracking and analyzing how this would work. Before we make commits, can you prevent issues? And you can clearly see it like from this graph that there's a lot of different issues that can be prevented from being even integrated into the code base. And so compared to the earlier one, to the baseline of the earlier one, which is that line that you're seeing here across horizontally, 80% of new bugs were prevented from being introduced compared to the original baseline of the tool running over that same code base, right? So that's significant. And so it means that, like over the years, we've been able to move, static application security testing, right? From being integrated in the testing mode, a QA team running it and so on, to something that can be integrated into the build, something that can be much closer to the developer and the code to be able to not only produce precise results, but also be very scalable, be able to run even in change sets. Now, at the same time, we also looked into some of the dynamic application security techniques. And here, you know, like a lot of people talk about fuzzers, right, as DAST type of techniques. One of the things that we realized is that not many people have focused on web applications. So we did a lot of our work studying in 2015, just purely focusing into web applications, because clearly, if you have a web application, that is a large attack surface. And now these days with cloud, well, that's even a bigger attack surface, right? So you do want to look into this. What were some of the challenges that we were seeing back then? One, the fact that automation was really lacking to be able to use this type of techniques effectively in a tool. And second, that there's a very inefficient use of compute resources. And if you're inefficient in your compute resources and you have, you know, fixed amount of money and time and compute to be able to run your fuzzer, of course you're going to be missing vulnerabilities because you run out of time to keep on running them, right? Now, DAST techniques do tend to run like more as a testing type technique because of their overhead, right? And in order to look into automation, like how can we make some of these techniques be automated rather than relying on we need to have a security researcher or a developer that is skilled in being able to run the fuzzer and then being able to do everything manually. Instead, wouldn't it be great if this can be done automatically? We point our new fuzzer to let's run this application, and then you start crawling the application automatically and start generating results for us, right? And so that's what our project Gelato was actually focusing on. And the aim was also to be able to automatically generate a Swagger or OpenAPI spec to be able to drive all of those inputs into existing fuzzers, right? So you can imagine that if you have like a REST fuzzer, any REST fuzzer, right? If you combine that particular REST fuzzer that is able to go into REST services and therefore go into different endpoints, right? You combine that with the techniques of automatically crawling through your web application. So that's like the outside blob that you see here of Gelato with the REST fuzzer. What you end up seeing is that now you're able to crawl various different types of web applications, and you can do this automatically. You don't need to have a developer or a security researcher driving that fuzzer. All of it can happen automatically, and you can start finding various different types of vulnerabilities. And actually interesting, when you find the vulnerabilities and you report them back to the development organization sometimes, like the developers themselves, did not know certain endpoints were available, right? Because it was not their intent, but it just happens that through crawling, we can do here's the dump, and here's how our crawling actually got to that endpoint. And it means that anyone out there on the web could actually also get to that endpoint. Now, another thing that we did, and this was combined with another project, Affogato, was to look into how do we make sure that we make better use of the compute resources, right? And so we started looking into gray box fuzzing, right? So gray box type of techniques, because with gray box, then you're able to help drive the fuzzer into which areas you should be looking into more, rather than having a black box approach, which is traditionally what most of DAST techniques are going to do, whereby you're blindly kind of like keep on going along various different paths, and you may not actually be increasing overall coverage. So the gray box approach helps us with that. And what that means is that if you take, you know, like say like the Gelato and the REST fuzzer technique that I talked about first, and then you compare that with integration into like a gray box type of approach, you get a significant reduction of compute time, of runtime that is needed in order to be able to find the same type of 0 days on web applications, right? And so in this case, we had like a runtime of 14 units. It went down to a runtime of 1 unit. That's significant because that means that now you can use all of that spare compute, either running your new combined parser further to be able to find other types of 0 days, or you could use that compute to run it on other types of applications and so on, right? So what that means is that, like over the period of like the last 6 years, there's been automation techniques that actually help you determine your attack surface automatically. Significant. You don't need to be like a security researcher expert to be able to do this, right? And at the same time, we've developed like new techniques that allow you to more efficiently be able to use all of your compute resources and hence be able to find more 0 days with a fixed amount of budget of compute resources and time, right? So, given those changes, right, what can we do to build an intelligent application security future? And here, we want, like the thinking initially was the fact that we were shifting a lot of things more towards the left, right? Like we want to be closer to the developer. We want to be able to help them more. How do you start giving them actionable type of input so that they can do more, right? We know that over time, the number of vulnerabilities of CVEs that get reported on a year-by-year basis has been growing. And this data comes from the National Vulnerability Database. The number these days is starting to become exponential, and these are new vulnerabilities, 0 days, that are being exploited in products on a day-to-day basis, right? So if you have like, let's say like 14,000 like new CVEs in 1 year, well, that's 14,000 different types of products or applications that are that can be attacked, right? And each product you can imagine is being used by thousands, if not millions, of people, right? So that's the impact of these vulnerabilities. Now, clearly, vulnerabilities exist all over, like the systems and the application stack. There are examples of vulnerabilities at the hardware level, right? Like Spectre, Meltdown, L1TF, like all of this started like a few years ago, right? Then at the OS level, traditionally, you have your operating system type of issues, like your buffer overflows, use after free, and so on, because a lot of code is written in C. Then you have like your virtual machines, you have other types of issues, containers, applications, and most developers are familiar with like the SQL injection type of issues or your cross-site scripting issues and so on, right? Now, at the same time, we know that malware is on the rise. And with malware, like the volume of malware keeps on going up and up. This is like very recent data, like from February last year, posted by Sonic Wall. And you can see there significant volumes of malware happening these days. Now, at the same time, you can imagine that you have your cloud systems these days. With your cloud systems, clearly, like the attack surface has increased, but also like malware, like is another way of being able to attack these systems. So it's not just only your vulnerabilities now, it's also all of this malware. And you can see it there, like the most common type of attack against like some of these cloud systems is malware, 26%. So that this data from Thales from June 2022. So if we look at the DevOps model and we think about security, you would have all heard about like DevSecOps, right? How do we introduce security into the DevOps model? Well, we need to look into security at all of these different stages. So I looked into like what does DoD actually say about this, because they have like an enterprise DevSecOps reference design. And clearly, like they do want to make sure that people introduce security into like their DevOps model and be able to focus on how to do testing and security by shifting left, right? And when you look more closely into their document, a lot of what they were talking about was, let's integrate SAST, or static analysis techniques, into the build. Let's integrate DAST, the dynamic fuzzing type of techniques, at testing time. And let's also look into interactive application security testing. So that's more of a combination, kind of like static and dynamic techniques. Integrate them at testing time. But you can clearly see that there are big gaps here because this is not covering the whole of like the DevOps model, right? And really, we should be removing like the whole testing concept from application security testing, because we need to be doing application security at all levels, right? It's not a testing type of thing. And when you look at a lot of the different types of tools that are available in the marketplace, and I mean, like this data was true even 3 years ago, right? There were not only SAST, DAST, IAST type of techniques. There was also software composition analysis. How do we look into all of the vulnerabilities that are coming through third-party libraries? There's also like web application firewalls, right? Like WAF, being used significantly, like in industry. And then there were all of the new techniques on Runtime Application Self Protection, or RASP, right? And if you start placing those techniques overlaying it onto this DevSecOps model, what you can see is that this is starting to look a little bit more closely to some of the examples that I gave you earlier on. However, the examples that I gave you at the start of the talk did not address security. And really, that's what we should be doing now. So let's think about it. What would intelligent application security really look like? If you look at the coding stage, being able to provide intelligent security coding would be something like a tool that can tell you you have a bug or a vulnerability at line X, and here's how you can fix it. So the intelligent component is that actionable item that we're providing back to the developer. We're not just saying, you have a bug, you go and figure out what to do about it. No, we're actually telling you, hey, there's a bug, but here's how you can potentially fix it, right? And doing that, obviously, before you commit, so much the better. Here's a different example, and this one is more relying on the third-party libraries. You're depending on vulnerable library foo, and that library has a vulnerability. You should be using instead version XYZ of the same library to be able to prevent use of that particular vulnerability, right? So in that case, you can now see you're starting to have like need for a knowledge base to be able to do those type of computations and be able to determine what would be the right version of the library in order to provide that information to your developer. Another example would be, like the library that you're using actually contains malware. Here's like a clean version that you should be using. And for that, you can see that compared to the earlier slide on the top right-hand side, your knowledge base, the inputs into your knowledge base is what changes, right? You're collecting all of this data from different places. Now, what about like during testing time? A lot of people you saw, like from some of the examples, Sapiens themselves, automatically generating a lot of test cases. How about we start focusing on generating test cases for security, right? Because a lot of the test cases that get generated is more from the development point of view, like, is my functionality the functionality that I want to have in my application? Well, let's start thinking in terms of like security testing. Have I included like the right security paradigms and so on into my application? So we could think about automatically generating some of these cases. And you can also imagine that if those security tests are going to fail, being able to propose fixes for them would be fantastic. And we would end up going back onto coding, right? At the same time, like you can also have these tests that check on your containers, because these days a lot of containers get deployed. You have various different pieces of executables in there, right, at the end of the day. And if you happen to be depending on some particular library that has malware, again, it's the same type of problem, right? Like this needs to be provided to you, like, hey, make them aware that there is this dependency on some library that has malware or some executable that actually has malware, and then be able to upgrade to a different version, right? And so how do you actually check for malware when you have executables in some of your containers? These are techniques, you know, that were developed long time ago when I was doing my PhD, right? Through the compilation type of techniques, you can actually look into your executables. And these techniques these days are integrated into tools like Gitra from NSA that allow you to be able to go through the executable, be able to find malware, all of these signals that you get, like, oh, yeah, this really smells like malware, someone needs to look into it, right? So there are ways to be able to do that. And further, last example for intelligent security testing is the fact that you could autonomously start generating allow lists for whatever your application happens to be doing, right? It may be that you have particular types of vulnerabilities that your system is prone to. Why don't you generate an allow list? And one of the classical examples that we use internally for our own testing is Java deserialization, right? That it doesn't only apply to Java. Of course, in Python, you also have like pickles, right? And so you have this deserialization type of vulnerabilities that can be attacked. And they get attacked not just by the code that you wrote, but the fact that you have other libraries embedded in your application. And so they make use of this combination to be able to prompt a particular attack over your system. So how about, like, the best solution normally is to use an allow list to ensure that some of those other libraries are not going to be used for the purposes of Java deserialization, right? And so this can be generated automatically through program synthesis type of techniques, right? Now let's move on to the right-hand side. Like during monitoring, one of the things that would be fantastic to do is to be able to look into how to autonomously be able to block attacks, right? So let's say that your application is prone to an SQL injection, right? Well, if that particular SQL injection is actually going to be attacked, this is something that if you're monitoring your application, you would know before executing that particular SQL statement, right? And so you could actually decide, I want to block the attack, right? And be able to make changes to my application, right? Or maybe I don't want to block the attack, but I immediately send out like all of this information to the relevant ops team for them to be able to do something about it, right? But now I have also the fact that there was an attack. I know the data. This is data that I can feed back into my testing process, right? This is data that could then be fed back into the coding, right? This is all very useful data for developers at the end of the day as to how their applications are actually being attacked, right? But you have various different things that you can do here. You can imagine that if you're blocking the attack, you can actually autonomously also update your allow list, right? And there is where like you can do like a lot more than just purely how we view a lot of things today, right? And in this particular case, you're seeing that the actionable items in this particular case, if you start doing things autonomously, is really doing it at the operations point of view, right? It's not necessarily that data always has to be going back to the developer, right? It can also be doing it with your own system automatically. Now, one of the things when you have, like an organization is that you're going to be running through a lot of different types of applications, right, and data formats and so on, right? And everyone runs email, everyone runs a lot of different types of documents and JavaScript applications and PDFs and so on. And what's interesting to see is that when you look at malware, like some of the file types where you find like a lot of malware, your executables, like when you're using like Windows, so this is very specific to Windows, your EXEs, that's the most popular one, but also like your zip files, also like your PDFs, your Office documents, they end up being like a large percentage of where malware can actually be hidden, right? And if you think about like your email client, well, how many PDFs do you get via email? How many Office documents do you get through email? Do you get any zip files and so on, right? So you need to start thinking also in terms of like through the normal operation of various different applications, malware can actually be injected. And therefore, being able to do like intelligent security monitoring at the monitoring stage is something that can actually prevent a lot of that malware from actually being activated in your laptop or some server somewhere else, right? And clearly, like in this case, you know, like any such data would need to be sent like to your SIEM, and then your ops team can actually start doing something about it, right? So if we put all of those examples together, this is the tomorrow that we envision at Oracle Labs. Be able to have intelligent application security all the way through. There's a lot of different aspects to it, right? You could be doing intelligent security coding. There could be intelligent security testing. That security testing could actually be proposing fixes automatically for you. You could also be doing intelligent security monitoring, being able to block attacks at the same time, being able to provide that attack data so that it can be taken into account back into the development process, right? And of course, on the top right-hand side, what you're seeing is a knowledge base that is very, very rich, right? Throughout different examples, you keep on adding more and more different types of inputs to be able to have a very rich knowledge base to be able to fit in and hook into all of these different areas. So what would be the definition of intelligent application security? This is a definition that we were working with back in 2020. It really aims at providing an automated approach to integrate security into all aspects of application development and operation. Doing this at scale, that's very important. Using learning techniques, and here learning techniques is not just machine learning. What I'm talking about, like program synthesis, is another example of a learning technique, right? So being able to integrate some of these techniques that come from the programming languages community, from the machine learning community, from the data analytics type of community, all of these learning techniques to incorporate signals from code and beyond, because your code today is not just the code that the developer writes, it's the whole ecosystem of everything that you import and where it runs, right? To be able to provide actionable intelligence to developers, security analysts, operations staff, and autonomous systems, right? And the key here is actionable intelligence, right? So what is it that the developer would do? What is that the security analyst could do about this? The operations staff, what could they do about it, right? And your autonomous system. Clearly, what this means is that we need to have like a closer integration of data produced by code analysis type of tools with the build integration, the testing, the operations, and any external sources that are needed. But at the same time, we need to have like teams that are providing the data and consuming the data be able to integrate themselves a lot better, right? So let me recap. In the late 2000s, there were various different challenges with static type of techniques to be able to find bugs and vulnerabilities, too many false positives. Runtime was very, very high. throughout developments that have happened over the last 16 years, we can now get very good, precise results. And at the same time, we can have a lot of scalability, be able to integrate early into the development cycle. And that is good. With dynamic web application type of techniques, the challenges were really the lack of automation, always needing to rely on a human to be able to run all of these fuzzers, as well as the inefficiency of the use of the compute resources. And over the past 6 years, there's been techniques that we've developed to be able to have automation over the attack surface detection, which is significant improvement from where we were, relying always on humans to be able to do this, and very specialized people like security researchers. At the same time, we've also managed to be able to have techniques for making better use of compute resources. So therefore, that means that you can find more zero days, and that's good because you want to find them before someone else finds them. Today, the DevSecOps model is all about how to integrate security into the DevOps approach. Now, clearly, you've seen it, and we all know that learning-based techniques have ripened over the last 10 years. We're seeing it in every place. And security these days is not just for expert developers. Security is something that is important for every developer, everyone. And automation is key given the size and complexity of our systems today. So it is really time to combine program analysis, learning-based techniques, and data analytics to be able to make intelligent application security at scale a reality. Thank you.
Thank you so much. That was a wonderful talk. My question is, are there any intellectual property concerns that are on your radar with using large language model learning, such as at code compile time, like with GitHub Copilot, but especially with some of the new techniques that you've mentioned? So for many companies, many developers that don't have their own large language model, that rely on something like OpenAI or GitHub, etc., do you have any words of advice or thoughts on the IP dangers there?
Right, yes. So when you're using, like some of these open systems, then like the main issue, of course, is IP. You're already sharing like your ideas. In a way, you're disclosing your ideas to the owners of the system, right? And it's kind of like what Simon was saying in the previous talk, that, by you disclosing certain things, then, they realize what's becoming common, and then someone else is the one that ends up productizing that, right? So for organizations and also like for startups, like people that do need to rely, for example, on patents, that becomes an issue as well, right? Because you're already disclosing the ideas, right, to someone else. And that means that then you wouldn't be able to patent if that's something that is important for you, right? And so I think like that is something that one needs to think about when doing, when using like all of the systems that are open, right? Like with LLMs. Now, it doesn't mean that you can't create like your own type of systems, right? And a lot of the work that we've been doing, we've been creating a lot of these knowledge bases ourselves, rather than relying on other knowledge bases, because then this way we're also composing the data that we want to compose as we see fit in order to further develop the techniques. All right.
Hello. Thanks for all the work y'all are doing pushing ahead these analysis tools. One thing I noticed is that these are tools specifically designed to integrate in like a traditional development product cycle, but there's a lot of applications these days being built that have very unusual environments. As an example, over the last decade, we've seen a lot of blockchains, right, that are coming up with these very intense security environments, very particular security needs, and if you're deploying a smart contract, you might want to do some different kinds of analysis. Or other people here are creating peer-to-peer networks. Other people are creating decentralized things where, like, your browser talks to another browser and all sorts of stuff. And so these things are a little harder to get visibility into in the more like traditional DevOps process. And I'm wondering if y'all are thinking about that, or if you have some answers for that, or like what's just kind of the vibe in that direction,
Right. Well, you can think like with blockchains, it is something that we looked into a little bit, and then we realized, but it's a little bit more of the same. And so we didn't actually end up doing work in that space because of that reason. With blockchains, for example, like when you look at the security, you can apply like a lot of program analysis type of techniques to be able to actually determine what would be like the types of issues, like the vulnerabilities that would be common in a blockchain, depending on whatever language, is being implemented for that blockchain. And so then what that means is that you can actually do that, like the same DevOps model and DevSecOps model would apply to the development cycle, right? Of course, the operations, that's the part where it would change, right? Yeah. And then for the operations, one would need to, like extend, kind of like change some of the dynamic techniques to be able to deal with it. Yeah. But for the first part, like the development of the code, like the testing and so on, there's a lot that it's a bit more of the same. Yeah. That's right.
Thank you, Cristina. It was awesome. Thank you so much.
All right. Thank you.